So please ask questions whenever they come up. Works a little better that way, and make sure that we're covering things that people are interested in talking about. And we'll have a little bit of time for questions at the end as well. So I'm going to talk about validation. Why would you care about validation? So we'll be talking about a few things to indicate why that might be important. There's a bunch of really cool stuff that we're doing in the Linux kernel community, and a lot of other open source communities are doing similar things. But I think we'll see that in the future we're going to need more. And I'm going to talk about a few possible ways that we'll be able to support this for concurrency. One thing is that validation is very much not a one-size-fits-all proposition. We always have had, and we probably always will have, one-off hacked-up scripts where you just kind of write the thing, it does its job, it probably has bugs, but if you didn't hit them when you ran it, that's fine, you're getting rid of it, and that's that. At the other extreme, we've always had and probably always will have systems that require extreme validation. Mission-critical business applications, people get really upset if they lose that much money. You may have seen some signs of that in the past 5 years or so. There's high-volume consumer applications where you might have a really low probability of failure, but if you're selling 1 million units, then having 10,000 of them fail may have really bad effects on your business and your reputation and everything else. Autonomous space exploration systems. Now, they're getting pretty good about this. They're actually able to upload code to Curiosity on Mars, which is kind of impressive. It's a bit of a long-distance phone call for your download. Or is it upload? I don't know. Load some direction or another. But, if Curiosity isn't able to point its antenna in the right direction, you're done. I mean, if you got a bug in where it's pointing its antenna, you can't talk to it anymore, and that's that. So there's some parts of that that just have to be right. No ifs, ands, or buts. You need really extreme validation. And of course, there's any number of safety-critical embedded systems, and you can lose lives if it fails. And we had an example yesterday in the kernel with the, I believe it was Ben Harrison was talking about pacemakers that might have security holes that could be exploited to have the same effect, even if it was operating correctly. So we need a pretty wide range. And one question might be, how do you tell where you are? This is kind of a partial list of the things I've worked on over a long time. And I'm not going to go through them in detail, except to note that the number of users is rather low. All right, the biggest project for the first couple decades I was working on had 100 users. And with those projects, there wasn't a need for any really violent formal testing. Because the number of users were so low, they used the system in very set ways. And so pretty straightforward, simple tests sufficed. And that was particularly important in the university housing system. That was on a timeshare system. Testing cost money. Using the computer at all cost money. And if you did too much testing, your customer got angry at you because it cost too much money. So there are trade-offs. But in the 1990s, I took on a different role. Went to work for a company called Sequent that did a database server system, parallel one. And we had up to about 6,000 sites. And it was doing mission-critical things. It was used heavily by businesses, their quarter close, and sometimes their manufacturing depended on it. And suddenly, we really needed a lot more formal stress and unit tests and also a lot of the heavy-duty stress tests. We call it TLB test rather than RCU torture, but it did the same thing plus a few other things. So part of it is just how many users you have. So going from 2 digits of users, less than 100 users, to about 10,000 users made a big difference in how I did testing. So what are we going to say about the Linux kernel right now, which over the time I've worked on it has risen from, it was at least 1 million users in 2000. I don't know how many. Now, if you count the smartphones, if you count Android, it's got to be at least 1 billion. And so the question that this is looking at, that I'm looking at here, is what the heck do we do now? Going from about 10,000 to about 1 billion is 5 orders of magnitude. And that might possibly require some changes in the way we do validation, maybe. My philosophy has been kind of the same. You want to torture your code to the best of your ability, because if you don't, it's going to torture you. And it's pretty good at doing that. Bugs have a tendency to pop up when you're wanting to do something else or wanting to be somewhere else, or when you're not available and people get upset. And this may sound kind of strange. It seems kind of mean. You're torturing Tux there and beating him up. And that, just doesn't feel right. On the other hand, I've had Tux torture me a few times with a few bugs. And we have heard in this conference a few other people have had similar experiences. And it's better to get it right to start with. Of course, testing has limits. Testing is great. I use quite a bit of testing myself, some pretty heavy-duty tests, I think, although other people may want to do better. But you pass this stress test, and well, maybe you just got lucky. In fact, I had a recent example of this in RCU where I had a bug that's been there for about 5 years. If you use certain configuration parameters that were perfectly legal, RCU would just not work. And it wasn't anything subtle. It wasn't like the typical things I've had in the past where you get maybe a failure or two in a 10-hour heavy-duty run. It was like failures per minute, okay? And I've blogged on it, but the thing is that if you, and the problem I had was I had an error in my test scripts, and there were a bunch of situations I wasn't testing that I thought I was. So when I improved my test scripts, I found this bug. So testing is useful. We need to do it. We need to continue to do it, but it has limits. And one of the limits we have, the general idea, what you're trying to do here, is to torture the code at least as much as the real world, as your user base is going to torture it. Because if you can put 10 times more stress on it than your users are, aggregate, you got a pretty good chance it's going to work fairly well in the field. If you got 1 billion instances running out there, it's really hard to torture your code more than those 1 billion instances running in parallel are going to. All right? And so one question, which we'll get to in a little bit, is why is Linux working reasonably? Why is the Linux kernel working reasonably in all these different areas? I mean, it's not like phones fall over all the time. They seem to be working fairly well. I haven't seen people, I'm not sure what kind of screen of death you get on an Android phone, but I haven't seen a whole lot of people getting those. The thing is, if you don't do that, if you don't put more stress on your code during validation than the real world puts on it, you are going to have bugs escape to the field. And to some extent, it's unavoidable. Nothing's perfect, and it's not going to be. Life is inherently imperfect, but we'd like to keep it down to a dull roar. And of course, some of those bugs will result in security exploits. I don't know if anybody has managed to do a security exploit based on an RCU bug, but it's just a matter of time, right, before something shows up. On the other hand, one of the reasons we have been doing fairly well is the Linux kernel community does use some pretty heavy-duty validation. It's of the projects I've worked on throughout my career, it's the one that takes validation the most seriously, even in some fairly impressive mission-critical things. So it's worth taking a look at what we're doing. And this brings up the question, okay, we've got these billion instances. We don't, that's doing 1 billion machine hours per hour. And we don't, as far as I know, we don't validate that heavily. I don't know if anybody has a test farm that's doing 1 billion hours per hour of validation. Maybe there's one out there, but I haven't heard about it, and it'd probably be obvious. And we know that the size... I'm sorry? Isn't that called users? Well, that is one way you can do it, is to just outsource your testing your users. But I found that my users aren't necessarily as respectful of my time and my other plans as my test farm might be. But that is one approach. They tend to run across a bug at some random time when I'm not necessarily prepared to deal with it, not happy to deal with it, but you got to deal with it, right? Anyway, the thing is that you might have a bug. Maybe have a bug in RCU that shows up every 1,000,000 years of runtime. Okay, 1,000,000 years of runtime. So you run this thing, and if you run it for 1,000,000 years, the bug might show up. Well, across 1 billion instances, that means that bug is showing up 3 times per day across the installed base. And I'm pretty proud of RCU torture, but I don't think it is good enough to catch 1,000,000-year bugs at this point. And some bugs do get through. I've seen examples of them where I've managed to get. Mostly, I think it gets out to distro testing, but I'm sure there's some that have made it to the field. So why is this working? One reason is that the bulk of Linux's user base, Linux kernel's user base, has a very small number of CPUs. And what happens is that we have big systems, a fair number of them, where we can catch bugs that happen fairly often on larger systems, but on the smaller systems that make up most of the installed base, they're much less probable. You know, the more CPUs you have, the greater the probability of a given concurrency bug occurring, all else being equal, which of course it isn't, but there you are. Unfortunately though, or maybe it's fortunately, but what is happening is these small embedded systems, their CPU counts are increasing. And that means that that advantage we've had, where we have big servers that have put a lot of concurrency stress on the system, and that protects a very large number of smaller systems that have less concurrency stress, that is deteriorating. That's going away with time. One thing that's happened with, yes?
Isn't that only true if the number of CPUs in small systems is going up faster than the number of CPUs in your larger systems?
So isn't that true only if the number of CPUs in the small systems is going up faster than the number of CPUs in large systems? That's an interesting question, but it means the one thing is what's faster mean? Because the smaller systems are going from like 1 to 4, 8. And the larger systems may be doubling as well, but they're out further. So, you know, maybe. You might be right. I'm not quite that trusting. But I hope you're right. It'd make my life easier, but I'm unwilling to trust the luck quite that much. One thing that's also has helped in the past, especially for the embedded market, and there's a huge amount of the instances of the Linux kernel running in the world are embedded one way or another, TVs, smartphones, whatever. And the nice thing about that is you can run a system test for that device that exercises what that device does fairly thoroughly. And when it's out in the field, it doesn't do much else, and therefore the bugs that are available are very likely to be found in that fairly restricted test. And that's wonderful, except that these embedded devices, over time, are becoming general purpose. I mean, you've probably seen internet posts about the smartphone being the new desktop. Well, if it's going to be the new desktop, that means it has the desktop variety of workload, and suddenly a restricted system test isn't going to be as effective at finding problems. Fortunately, one of the nice things about the kernel community is there's a lot of tools, testing, and validation going on. So it's worth, yeah, or...
Talking about scaling CPUs, the big systems generally aren't ARM CPUs, and the phones are generally ARMs.
Mm-hmm.
Does that have much impact on what you can learn?
So the question was, the big systems tend not to be ARM, and the little systems tend to be ARM. And you know, does that make it a little more difficult to take your learnings from the big system and apply it to the little systems? And clearly there are some limitations. The big systems aren't exercising Arch ARM very much. And so whatever bugs are there are going to have to be found within the confines of ARM. On the other hand, there's a lot of core kernel code that's fairly aggressively parallel. And that gets shaken out pretty heavily by the larger systems. But yes, you're right. There are parts of it that do change as you go down to the smaller end. So it's worth taking a quick look at some of the testing and tooling that is helping. One thing, of course, is code review, the old thing about all bugs being shallow to 10,000 eyes. All bugs being shallow to 10,000 eyes. That's fine, except I'm not sure the review has really kept pace with the change rate and the complexity. From 3.11 to 3.12, there were over 8,000 files changed, 500,000 insertions, and 250,000 lines deleted. So if we were going to have 10,000 eyes on each line of code, well, 500,000 times 10,000 divided by however many lines somebody can review in a few months. I don't think we have that many people doing reviews. But still, code review is very important, and there have been a lot of very subtle bugs that have been found and fixed because of review. It's something we need to keep. It's just that it can't be the only validation thing we're using. We have to have other things as well. And the good news is we do have other things. There's unit and stress tests are becoming more common in the kernel. I'm, of course, proud of RCU Torture, but there's lock tests, kernbench, hackbench, and so on. Linux test project, Dave Jones' Trinity has been quite effective in the last couple of years, finding all sorts of interesting bugs by intelligently fuzzing the system call layer, by randomly generating system calls, but with some intelligence based on what other system calls happened more recently to force code paths that make sense. There's also automated or recurring tests. Stephen Rothwell's -next testing has been around for a while, and I think it's done a really good job of doing integration testing for for the stuff that's going to go in the next merge window. Feng Guangwu's K-test build robot is something that does individual tests, and it's been very helpful to me. And of course, there's just a lot of other testing going on. There are some tools that have been helpful. Sparse is one. Lockdep has been extremely helpful over the past 5-10 years in finding deadlocks and so on. And I think we need to really give a big thank you to everybody who's been helping with this. There's been a huge amount of work, and a lot of this has been helping allow the Linux kernel to work well, despite this mismatch in the testing versus the installed base. And for those who haven't seen it, this is kind of what, if you push a change out, push a commit out, and there's a problem with it, you'll get an email automatically like this. In this case, I hadn't tested a certain configuration, and I got a build error out of it, so he complains about it. And furthermore, one thing that's nice more recently is he actually flags which line of code has the problem. So it makes it kind of nice. You don't have to go check it out, and go look for the thing. You can just look at that and see what's going on. So all those things are very helpful, but things are likely to get more vicious in the future. It might be that CPU counts have increased as far as they are, and they're not going to increase farther, but that would be a surprise to me if that happened. And that includes the low-end systems, that many of which are a single CPU or a very small number of CPUs that will be increasing in scale. The other thing is that as the larger CPUs get bigger, we'll have to use more of the aggressive scalability techniques. And that means going away in some cases from strict locking. And the problem is things like lockdep don't help much with atomic operations or memory barriers being misplaced. Right now, that sort of inspection is manual. Now, perhaps we can improve the tools to check for that, and I'll talk about some possibilities later on, but and just manual inspection is wonderful, but it doesn't scale. So we're going to need some way of automatically checking for these things, possibly extending lockdep, which it has been extended. It now checks the various things in RCU and so on, for example. And of course, there's a lot of other needs besides just concurrency, like validation against standards, to say nothing of validations of standards themselves. But because I know about concurrency, I'll focus on concurrency for this presentation. So one way of looking at this, what I've been doing is not just looking at the failures that hit the field, but also the near misses. And this is kind of by analogy with airplane safety. They don't wait until airplanes actually crash before they complain. And in the Linux kernel, we need to take the same strategy, and we have. Lockdep, for example, doesn't wait for a deadlock before it complains. Instead, it waits until the conditions are set up that says, geez, there's these locks, and they're acquired out of order. Therefore, there could potentially be a deadlock, and then it complains. So, some near misses. One was a RC CPU stall warning bug. It was a shortcoming in my development methods. The way this works, what it's doing is that if a CPU does something like spin with interrupts disabled for like 21 seconds, okay, which is a long time to have interrupts disabled. This does happen from time to time, okay? I mean, it's then RCU complains and says, that CPU is not talking to me. Maybe you need to take a look at it. And the thing is, 21 seconds is a long time. I mean, I shouldn't have to be dainty about checking for something that's taking 21 seconds. I've spent the last 2 or 3 years learning how wrong that statement is. I don't care if it's 21 seconds. I have to be just as careful with checking for RCU CPU stall warnings as I do for the core CPU grace period mechanism. In early days, I was fooled by the fact that it was not on by default, and so there were relatively few of them. Since it got turned on by default, they show up all over the place. And what that did was suddenly increase my user base from a few tens of people who cared to the entire user community, as Robert pointed out earlier. And I got a little bit of an education in the variety of things that could happen and what you had to do to make sure that you were giving useful information when the CPU stalled. Another near miss was caught by mainline testing. This was a fun and exciting one in 3.0 RC7 with a race between RCU, the interrupts, and the scheduler. And the problem is that I had allowed RCU to become more entwined than it had to be with the rest of the kernel, which meant that small changes in other parts of the kernel had an outsized effect on me. And one of the things that I need to continue going forward is to make sure we maintain modularity so that we can avoid this sort of thing. There was a day one RCU initialization race I caught last year, which I'll show on the next slide. But I should say that actually day one is kind of a slippery concept in RCU. If I want to be pedantic, I can actually say that I've eliminated all RCU day one bugs, guaranteed. You see if you diff against, say, 2.6.12, there are 3 classes of statements still left. One of them is preprocessor directives, like self-excluding include files. The second one is comments, like the GPL header comment. The third one, blank lines. Very good. So there are no day one bugs in RCU, so I decided I better change the definition to be like when I first added that code as opposed to back from 2.6.12, since that's kind of meaningless. This is an initialization race I found in late 2012. I'm not going to go through it in detail. The slides will be up so you can look at it if you want to and go look at the commits. The point I'll make is it takes 3 CPUs to make this happen, and not just any CPUs. They have to be, at least 2 of them have to be in different sets of 16 CPUs. If you have less than 16 CPUs, so if you have 16 CPUs or less, this can't possibly happen. And you have to have 3 or 4 fairly rare things happen sort of at the same time, just wrong to make this happen. And this, as far as I know, hasn't happened in the field. The reason I found it was I made a change that made it much more probable, and then it started showing up all over the place. Now, I do have guys that review RCU, and they're really, really smart guys. Very impressive. But I can't expect them to find this. And that's asking a bit much, I'm afraid. I didn't see it until it whacked me over the head. So we need something to help with this sort of thing because these sorts of problems will be showing up. So it's hard to say exactly how we'll do this. What I'm going to be talking about right now is kind of speculative. There's a little bit of this I've done in the past, actually going back 20 years, but there's some work that might make it more useful or might not, but it seemed worth taking a look at and chasing down, and I'll be working on it some more going forward. One of the problems we've had with formal verification is that a lot of the formal verification guys had a very strange notion of what their job was and what systems did. So the traditional formal validation means that you validate all the behaviors of the entire system, and that means you need a description of all the behaviors of the entire system. And that description tends to be about as big as the system itself, and just as likely to have bugs as the system itself. And also, this is very slow. They've actually done this for a non-trivial, well, sort of non-trivial system, the L4 microkernel, which is about 10,000 lines of code, roughly. And the way they did that is they took a very large number of Russian PhD students, taught them Isabelle, which is a validation language, and locked them in rooms and made them beat up on this. And on a very good day, they might get 25 or 30 lines validated, but that would be a very unusually good day. So this takes a huge investment of time and effort, and it's not really feasible for 15 million lines of Linux kernel code. Yes?
L4 is still pretty basic too.
Yeah, L4, the comment was that L4 is pretty basic, and yeah, it's not, I don't think it's multiprocessor even. Maybe it is. But yes, it's not, and it's not 15 million lines of code either. It doesn't run on 1,000 CPU systems. So this is something that's interesting for very small pieces of code. I'm sure that people will keep doing it, but it's not something we can apply to the entire Linux kernel. They also want to assume strong ordering, and by their definition of strong ordering, x86 is weakly ordered. x86, if you do a store followed by a load, it can interchange them. And when they say strong ordering, they mean you don't do that. Unfortunately, if you make that restriction, your CPU runs very slowly. So most manufacturers want to have the store buffer optimization that allows that interchange to happen. And so we do not have strong ordering on any commercial CPU by the formal methods guy's definition. They also tend to want special purpose languages. And that's unfortunate because most parallel code is in general purpose languages like C in the case of Linux kernel or C++ in other things. So I was actually getting pretty kind of a negative attitude towards the formal validation guys until a couple years ago. I was at a workshop, and a guy named Richard Bornat, who's been in the formal validation since the 60s, emeritus guy, he's a prof in the UK. And he got up in front of a bunch of people and said, our job is to validate the code the developers write in the environment they write it in and in the language they write it, which I thought was pretty cool. And he's actually done some work with that. He and a bunch of students took and wrote a tool that generates pre and post conditions given C code. And they dumped the Linux kernel through it and were able to do that for about 1 million lines of the Linux kernel. Now, I have no idea what I would do with 1 million lines of pre and post condition, but the fact that they were willing to do something like that on a code base like the Linux kernel is actually a really nice change. And a number of researchers have been taking this to heart, a very small fraction of the total, but still a fairly large number. And I'm going to talk really quickly about what some of them have been doing and how that might in the future, I mean, the stuff is mostly not ready for prime time, but might in the future help us out. This one's been around for a while. I did a LWNet article a couple years ago on it. And what you can do with it is you can take short assembly language sequences. You multiple processors, so processor 0 does a store, processor 1 does a store, processor 2 reads those two things in one order, and processor 3 in the other order, and you give an assertion down there. And this tool will do a full state space search. It will go knowing the semantics of that processor, in this case power. They also do ARM, and I think the C++11 is another one that they do. And it will look at anything that those CPUs might do and tell you whether or not that assertion will trigger in any of those situations, which is useful when if you're trying to work a very small piece of a parallel algorithm and make sure it works. The nice thing is you can get definitive answers for some of these things. I mean, in the past, what you had to do is stare at the books, ask architects, and maybe you knew and maybe you didn't, and it took months. In this case, you can actually run it and see what happens. And it's actually especially for research code, it's actually pretty good. It seems to be near production quality in terms of what it does. It does have some shortcomings. It deals with assembly. You have to translate that. It does not handle arbitrary loops or arrays. Very small code sequences, a limited application, and it takes a while. Now, that example I showed on the previous slide takes 14 CPU hours and about 10 gigabytes of state space on a fairly recent x86 processor. So it's does chew up a little bit of time. The one I showed was one that worked, so it had to do a lot of validation. Failures can be detected more quickly. And it's not perfect, but it's actually a really cool milestone in real-world parallelism. It's a case of some academics actually saying, okay, what do the real-world programs have to deal with, and how can we help them with that? And that's a really nice change from previous projects. Of course, you're not going to dump the whole Linux kernel through that. But still, if you have a very short sequence of code you need to do some specific interchange or some specific synchronization, this can help with it. Another approach is something that's pursued by Alglev, Kroning, and Chashnig. The thing is that programming language writers are very proud of the fact that their language is Turing complete. But the fact is, if you're running an in-real system, it's a finite state machine. In fact, the universe seems to be a finite state machine, so there's some limits you have there. And the thing is that a finite state machine can be represented by a logic expression. And if you have an assertion in that, you can use a SAT solver to determine whether or not that chunk of code that got turned into a logic expression will ever trigger. Now, SAT is NP complete. Means that its runtimes get very large, increase exponentially with the size of the problem. On the other hand, full state space search is no picnic either. It's, if anything, worse. And there's been a huge amount of progress on SAT over the past 20 years. 20 years ago, the state of the art was an expression that had 100 variables in it. And that was just barely possible. And within the last little while, they've gotten to where they deal with million variable problems. If you're talking a million variable problem, that means you might actually handle tens or even hundreds of lines of code. So, this is very new. The papers on this were published like last year. And of course, they've got tools. They're publicly available, which is really cool, except that this research code, they did just enough to publish the paper. And there's a lot of work to go beyond that, but still, it's an interesting start. I'm not going to go through this in massive detail, but the basic thing is you might have a little code snippet like up in there where CPU 1 assigns 1 to x and then 2 to x, and CPU 1 just reads x. And what you can do is turn that into a logic expression that describes what could happen there. And again, I'll just go ahead and look at what it might look like, which is this mess down here. And a reasonable question to ask at this point is, how the heck is this supposed to make things simpler? And obviously, I can understand that a lot easier than I can understand that. But the neat thing is, I don't have to understand that for it to be useful. There's a lot of software out there to analyze these expressions, and the hardware guys have been doing validation using this kind of stuff for a long time. And they can all simplify and manipulate them. And the nice thing is they can generate them directly and automatically from C code. You can take C code and feed it to one of these things, and it'll go and do this stuff and also solve it. And that's, of course, a good thing, because doing this by hand would be totally impossible. Yes? Am I sure there's no bugs in the software analyzing these expressions? Well, as you'll see in a couple slides, I know really, really well there are bugs. It's research code. So one of the things that's actually been around for a long time, but only deals with sequential code, is something called CBMC, the C-bounded model checker. And it takes small C programs as input and does array bounds checking and also checks for assertions automatically. Again, it doesn't handle multi-threading, but it's a place to start. And this is actually fairly reliable. Seems to work pretty well. So I had to write a little program to check it out. The little program takes an argument, multiplies by 2 and adds 1. The result is guaranteed to be odd, and then it has an assertion saying, yes, it's odd. And to validate this with CBMC, you just go cbmc even.c. Just give it the C file, and it goes through, does all this stuff, and at the bottom it says verification successful after 17 milliseconds, which, not bad. Of course, to Matthew's point, how do you know you can trust your software that's doing this analysis? And one way, of course, is to hand it a bad program and see if it finds the bug. Okay, well, that's easy in this case. We just remove that +1 there, so we say we multiply I by 2, so it's guaranteed even, and then we assert that it's odd. And, if the software's working, it should yell at us about that, right? And sure enough, it does. It says verification failed at the bottom. I didn't show it all. It actually gives a trace, which I was really impressed with. It actually works backwards from the logic expression of the C code and tells you what lines of C code various things happened on for the bad thing to happen, which could be helpful. And just to be obnoxious, I had to do Fermat's last theorem. You check the bounds to make sure it won't overflow, and then you assert that a cubed plus b cubed not equals c cubed. This one took a little bit longer. It took almost 3 minutes to validate. And I mean, you could have actually exhaustively run the thing a lot faster than that, but then it would have taken me more than 3 minutes to write the program and make sure get all the bugs out of it. So I guess this was a win. The reason it was so slow is that I had multiplication in there, and stat solvers deal with Boolean variables. So the logic expression had a logic equivalent of a hardware multiplier in it, and a hardware adder, and a hardware comparison. So that's why it had 24,573 variables and 29,508 clauses in the logic expression it was analyzing, all right? So yes, if I'd had to do that massive logic expression myself, it'd been hopeless. But it seemed to do just fine with it. And if given that big, I can forgive it taking 3 minutes to figure that out. So, this looks like it has some promise, but of course this is still only sequential. This is kind of a summary of where you can get it, and it's got a really nice documentation and what it does. But how about multi-threaded, right? Well, it turns out these guys have produced a prototype, and I mean prototype in the, prototype, I'm telling you. But actually, it does a memory model, and it actually does ordering and does various constraints and single assignment. It's a little bit more complicated, but it's scripted fairly easily down there. And I became aware of this. I was at a workshop in Rome and this guy gets up and says he's doing this thing to check memory ordering. I'm going to go, okay, that's whatever. And then he told me what his test workload was for it, which got my attention. He said he was using the Linux kernel RCU implementation as his test thing. So of course at that point I asked him if he found any bugs, at which point he started explaining RCU to me. And I responded, he'd say X, Y, Z about RCU, and I say, okay, ABC too, and we did that a few rounds, and eventually it was clear that I wasn't getting across to him, I already knew it. So I said, you know, just so you know, I'm the Linux kernel RCU maintainer. At which point he said, oh, I guess I don't need to explain it to you then. Although sometimes I think I could use an explanation, but hey. Anyway, what these guys do, what they're able to do is they actually expand the logic expression to cover multiple threads. And you have to kind of include your program. This is the same program I had in assembly language before. The yellow stuff is the code under test. The white stuff is the stuff you have to put there to make it do what it needs to do. So I've got a variable I'm setting to 1, variable y I'm setting to 1. They both start out 0. I load in one order, I load in the other order. The unbuffered stuff is stuff that is not actually validated by the machine. It's just there for the assertion. And I guess it's not going to help to look at the other screen. I have to actually advance to the next slide. I have my assertion there saying that what I expect not to be able to happen. And it does just fine. The cool thing is it takes 2 CPU seconds instead of 14 CPU hours. And it takes maybe 10 megabytes or thereabouts, I couldn't really tell, instead of 10 gigabytes. So this is a really nice performance enhancement compared to the old state space search approach. So that's good. This is where you can get it from, how it handles it. It has the same thing that doesn't handle general loops. However, you can give it a parameter saying unroll your loops to like 5, and it'll go there. The problem with unrolling loops, with it doing loops generally, is that you end up with an infinite logic expression which the machines don't like to handle. So I just happen to have some new RCU code. It's covered. John wrote an article on Is the Whole System Idle? And we've done a bunch of testing on it and also some review, but you know, why not try this out? Why not just try this stuff and see what happens? Unfortunately, that happens. It's quite possible 685 lines was too much. I sent a bug report in and they found something or another, and maybe I'll get a fix at some point. But they've got another tool called Impara. It's very similar. I mean, it takes pretty much the same source code with different flags. First thing I found out is it doesn't like dynamic memory allocation. It yells at you on every malloc. There's a bug fix for that apparently in the works. But I can just use static allocation and just assign pointers, and didn't like that either. So I may have to fall back to problem with spin for this one. On the other hand, it did just fine with all of the memory ordering litmus tests that were, you know, if you have just pairs of variables and you do with them, it did just fine on all of those. So at the moment, it's a matter of finding out what it can handle. In the meantime, for the larger things, I may have to do problem and spin. But the really cool thing about this is if you can handle C code, I can imagine taking parts of RCU and putting comments in there. They're to be automatically recognized. Have a script that yanks the stuff out, throws it into the thing, and just does the validation as part of just normal testing. And that'd be really cool. And that might be possible in 3 to 5 years. This stuff is pretty raw. The paper was just published this last year. Okay, so there's a lot of stuff that has to do to get it to where it's going to be production ready for that sort of a thing. But the fact it can do what it does is a really, really nice change for what's happened, what we've been getting from the formal validation guys in the past. So validation of the Linux kernel has been increasingly challenging. That's likely to keep going for a bunch of reasons. The Linux kernel community has done a really good job of rising the challenge, but the hill is still growing, and we have to climb it. And these are some possible tools that perhaps might help us out in the future. And I think they'll handle larger problems than some of the other things have before, but time will tell. I'll still be playing around with it and giving a hard time to the authors when things break. This page is always sponsored by IBM Legal. And if you have more questions, I'd be happy to take them. Yes?
You said the state space search was, I think, 14 CPU hours. Is it a highly parallelized algorithm? Can we just go 1,000 if you use that, you get it done pretty quick.
So the question was, this thing that took 14 CPU hours, is it parallelizable? Can we throw more CPUs at it and make it go faster? Potentially. Right now it's sequential. The implementation is sequential. And if you could somehow work out what part, split the state space up, you could go in parallel. Promula has some features to allow parallelism, but you pay a price for that because suddenly you have to introduce locking and other overheads, and you may get a win, you may not. The key thing is that maybe if you use 1,000 CPUs, you get 1,000 times speed up, but I got like something like 10 or 10,000 times speed up by using a different algorithm. So, you know, I think we'll end up having to do both at some point. But yeah, there's a lot of work and performance is going to be part of it.
Time for one more question before we wrap up. If not, thank you for joining me in thanking Dr. Pomakin.
Thank you.